Hi guys, Justin here from chemistrynotes.com, and this is video number 2 on section 16. Section 16 is spontaneity, entropy, and free energy. And at the end of the last video, we were starting to talk about entropy, S, or delta S, if you will, the change in entropy. And entropy is the measure of the disorder or the randomness of a certain event, a certain chemical reaction, a certain process, etc. And at the end of that video, I mentioned that we would start with the second law of thermodynamics, and that's what we're going to do. So the second law of thermodynamics states that the entropy of the universe is constantly increasing. In any spontaneous process, the entropy of the universe increases. All right, so what specifically do I mean by this? Well, let's dig a little deeper. First, I want to reread the definition again. Second law of thermodynamics. The entropy, S, or the measure of the disorder or randomness of something, the entropy is constantly increasing. It's always going up and up and up. In any spontaneous process, the entropy of the universe increases. So the change in entropy of the universe is delta S universe, and that's equal to the change in entropy of the system, which is usually the chemical reaction, plus the change in entropy of the surroundings, which is everything in the universe except for the reaction itself. So if the change in entropy of the universe is greater than 0, the process is spontaneous. If the change in entropy of the universe is less than 0, well, then the reverse process, the reverse reaction, is spontaneous. And lastly, if the change in S, or the change in entropy of the universe, is equal to 0, the process has no tendency to occur. It's at equilibrium. Okay, either process is kind of at a standstill right there. I shouldn't really use standstill, but it's at some sort of dynamic steady state, a dynamic equilibrium. Now, if you see that little asterisk down there in the notes, it says sometimes delta S system and delta S surroundings have opposite signs. Now, if that's the case, then their magnitudes are going to determine whether or not delta S universe, the change in entropy of the universe, is overall positive or overall negative, and then some freak circumstances perfectly equal to 0. All right. So the top of page 2 of our notes here, underneath the little double dagger or the double underline, I have a new entry here, and it says entropy change delta S in chemical reactions. So let's take a close look here. It says entropy change in chemical reactions. And I got a little bullet point under the notes there. It says that we want to focus on the amount of gas molecules or gas particles or gas atoms, if it's noble gases we're talking about. You want to focus on the amount of gas molecules on the reactant side versus on the product side, because this is just, it's the quickest way to the answer on whether or not the entropy is increasing or decreasing when you look at a chemical reaction. And as we've mentioned before, gases have the most disorder, or the highest change in entropy involved with them, and solids have the least amount of disorder because they're the most structured. All right, so they have the lowest delta S, or the lowest change in entropy. And we've seen something like this before, this box, except now I've added aqueous. Aqueous solutions are slightly more random than pure liquids because we have solute interspersed around the solvent molecules as opposed to a liquid, which we could consider to be just pure solvents. All right, let's take a look at the example. Does entropy increase or decrease in the following reactions? Well, in this reaction, A, I see I have 4 molecules of gas on the left, only 2 molecules of gas on the right. Remember, gases they're responsible for the most entropy. So 4 gas molecules, quote, goes to or yields 2 gas molecules. Well, fewer gas molecules means fewer possible configurations, fewer possible. It's almost like it can require a smaller environment. So fewer gas molecules on the right-hand side of the reaction relative to the reactant's side means that my disorder here, or my entropy, is actually going to decrease. So because I'm going from 4 gas molecules down to only 2 gas molecules, we can say that the entropy of this reaction is less than 0. Entropy decreases. All right, B, our next example. We want to know, is the change in entropy here, is entropy increasing or decreasing when this reaction occurs? So on the left-hand side, I've got 9 gas molecules, and on the right-hand side, I've got 10 gas molecules. So we can say delta S is greater than 0. In other words, my entropy increases. It's a positive number. And that's just because we're going from 9 molecules of gas on the left-hand side to 10 molecules of gas on the right-hand side. Okay, so this is the opposite argument that we just saw for A. All right, so that was B. We just did A on the other page. Now let's move to another little star here. It says standard entropy values, S with a little degree sign. Anytime you see a little degree sign like that, and they're not referring to Fahrenheit or Celsius temperature, they're telling you 2 conditions. They're telling you that you are at 25 degrees Celsius, right, 298 Kelvin, and you're also at 1 atm pressure. Standard entropy values. Now, we did talk about the table I'm referring to here in your appendix earlier when we talked about heats of formation. But the heats of formation table usually has free energies of formation and standard entropy values. And S values are listed in lengthy tables in the back of your book. Sometimes it's not referred to as a table, but called an appendix. And if you are able to find your textbook or just go on Google and type in standard entropy values, you'll see long columns of all these entropy values. All right, and it says, notice, like for example, if you go to the entropy values for H2O gas, H2O solid, H2O liquid, you'll see that indeed S increases for a substance in going from a solid to a liquid to a gas. Standard entropy values have units of joules per Kelvin per mole. Joules per Kelvin per mole. So to calculate delta S for a reaction, we have this fancy looking equation, but I like the equation on the next page. But basically, the change in entropy for a reaction is just the sum of the entropy values of all the products minus the sum of all the entropy values of the reactants. In other words, here's my version of it. The change in entropy of a reaction, right, whether or not disorder increases or decreases for a reaction, is equal to the sum of all entropy values for the products, right, and you can look those all up in that table in the back of your textbook, minus the sum of all the entropy values for reactants. Now, one thing I've kind of not included here, and I'm going to put it in a bullet point right underneath, don't forget to include the number of moles of each reactant and each product. Don't forget to take the coefficients into account, right? Those big whole numbers in front of your particular reactants and products. All right, so it says, don't forget to take the number of moles of each substance into account. That's important. So, example, calculate the change in entropy, or calculate delta S for the following reaction. Al2O3 solid plus 3H2 gas yields 2 Al solid plus 3 moles of water vapor, H2O gas. Make sure that you know the states of each of these guys, because they're Al2O3 solid, H2 gas, but those are kind of obvious, and Al solid, but the H2O can also be a liquid in that table, so make sure you get the right value. And those values I've circled, they are all in units of joules per Kelvin per mole, and they are all from the table in the back of your textbook underneath the column where it has the little S degree sign, standard entropy values. So the change in entropy, right? If you refer to the box at the top of this page, I'm summarizing the 2 times aluminum plus 3 times water, H2O, minus the second bracket. And if I do all this, your change in entropy is equal to 179 joules per Kelvin per mole. All right, so I have a question. If 3 gas molecules goes to 3 gas molecules, how come delta S is large instead of nearly equal to 0? So if 3 gas molecules is going on the reactant side, is going to 3 gas molecules on the product side, how come the delta S value is large instead of nearly 0 joules per Kelvin? All right, and I've asked you a question, and here's the answer. The large delta S value is because H2O, which was the last product, the 3 moles of H2O gas, it's actually more complex than H2, which you probably would have guessed. H2O is a more complex molecule than H2, the simple diatomic, and thus water has a higher intrinsic entropy value than does H2. Okay, H2O has more frequencies. It goes through these different bends and things like that. So if the question were posed, why does H2O have a higher standard entropy value? And it's because H2O's molecular structure, right, being more sophisticated, has a greater tendency or greater ability to go through different types of vibrations or stretches or bends or rotations, etc. Okay? And that increases the amount of randomness associated with H2O versus plain old H2, right? Water has 2 bonds and 2 lone pairs on the central atom. Hydrogen is simply 2 hydrogen atoms connected by 1 covalent bond. All right, in the next video, we're going to start to dial in on free energy, and then we're really going to focus in on spontaneous reactions versus non-spontaneous reactions. Free energy, well, entropy has the delta S associated with it, right? Free energy is going to be delta G, and then we're also going to integrate delta H, which we learned in the past, okay, the change in enthalpy. We're going to get all these guys together, and then we're going to kind of hone in on spontaneous reactions a little bit more than just a simple discussion about entropy or the measure of disorder or randomness of a process. All right, so if you like the way I do these handwritten notes, all my notes are available at chemistrynotes.com. I have general chemistry notes and organic chemistry notes, and you should be able to find everything you need right there. And stick around, here comes video number 3 from section 16, Spontaneity, Entropy, and Free Energy. All right, see you soon.